Okay, let's start the second round of the debate. Okay, the opponent please propose a problem.
We would like to challenge you Pennsville Tower.
We reject Pennsville Tower.
We take the problem six. Problem 6.
We would like to challenge you candle power turbine.
We accept candle power turbine.
Candle power turbine. Okay, so problem 13. Candle power turbine. Richard, please go ahead.
Hello, I am Richard from Uniters, and I'll be presenting on the panel power turbine. So the problem statement states that paper spiral suspended above the panel start to rotate. Optimize the step for maximum torque. So the main focus of this presentation will be on what is the character of flowing air, what parameters affect torque, and what setup generates the maximum torque. So I'll be going through the phenomenon investigation, and then I'll go to the theoretical model, my experimentation and discussion, and my conclusion. So here's the video demonstration. As you can see, the spiral rotates slowly, it accelerates, and it starts by rotating slowly and it'll get faster and faster. But it'll eventually reach a terminal velocity because of air resistance. So I will first define what a spiral is. A spiral is a circular shape with an increasing radius made of paper in this problem. So I defined it with an equation most based off of r equals theta. It's just a constantly increasing radius. So in this example, I use r equals theta over 2 pi. I also defined a candle as a flame burning on a wick. And it does not have to be made of wax. So for example, that alcohol burner also counts as a candle. I assume that a candle generates a constant amount of heat, and that air resistance is negligible because I'm optimizing the setup. I'm not trying to quantify the torque. I'm just trying to optimize it. I also assume there's zero friction at the center of rotation, and the center of rotation does not move during the experiment. I also assume that all variables not mentioned remain constant, such as room temperature. So first, I will need to explore what a linear drag means, because it could be the model for our theory. So the Stokes law states that force equals 6 pi mu the radius times the wind speed. And linear drag states that the air would drag along the bottom of the wing of the spiral, and the force would rotate the spiral counterclockwise if you look at it from a bird's eye view. Quadratic drag is the opposite. It depends on, it's based on Rayleigh's equation, which states that half rho v squared CD and the area. It states that the air would bounce off the wing and it would spin the wing in the opposite direction, clockwise, if you look at it from a bird's eye view. I also explored how vorticity would affect the torque. Because if the drag is based off of Stokes' law, then viscosity would matter, and with viscosity, a vortex created by the flame could potentially affect either speed up the spiral, which generates more torque, or it could also slow down the spiral. And there's also vorticity in quadratic drag at the ends of the spiral. So like when air, because there's a different velocity traveling across the top of the spiral and the bottom of the spiral, they're traveling in different directions and also at different speeds. So there will create a vortex at this edge, which could potentially twist the spiral as well. So our theoretical model. So first, our drag is quadratic because we notice that the spiral is turning in a clockwise direction. This means that Stokes' law and its derivatives, such as shear stress, is negligible. They don't matter because the spiral is not based off of Stokes' law. And Rayleigh's equation is used in our theoretical model. So here's how I derived the model. I calculated the momentum in the x and y direction, and then I translated it to force. I also assumed that because I need an area to calculate my torque, and the area of interest. So I assumed that the average radius would work as a radius for my spiral instead of integrating the area of the spiral itself, because I found numerically that the difference is negligible, and it's often best to keep things simple. So here's my, after simplifying and substituting, here's my overall torque equation. So torque equals rho, which is air density, pi v squared, v is wind speed, and my r outer plus r inner. R outer is the outer radius of the spiral, r inner is the second radius of the spiral. So this is just part, like, r outer minus r inner over 2, which is supposed to be plus. That's the average that I use to calculate the area. I have sine 2 theta and cosine theta. The thetas are the slant angle, how much the spiral is slanted, like this angle. So I can derive a few parameters from this equation. such as wind speed, air density, the radii, the length of the lever arm, and the slant angle. So other parameters I can derive from these first initial parameters are altitude and temperature, which affect air density, the rigidity of the spiral, which affects the slant angle, and the area and height, which affects both wind speed and the length of the lever arm. So I'll move on to my demonstration. For my I use, for forming my spiral, I use a laser cutter with a vector image to cut out a spiral out of paper. And I use tracker to get my data. So I neglect a few parameters. I neglect the changing state of the spiral, such as the rigidity of paper, because that's just impossible to quantify. I'll explain further in the next slide. I also neglect altitude and air density, because I can't exactly go to Mount Everest and do this experiment, and then go to some low altitude place and do the experiment. The difference between the fourth floor, which is where I normally do my experiments, and the first floor is negligible, so I just completely ignored that parameter because it's not realistic to test. I also neglect fluctuation in wind speed, which relates back to my earlier point about heat being constant, because statistically the fluctuations in wind speed would eventually average up into one average wind speed. For my rigidity, because heat softens the paper, the slant angle would always be increasing as I continue doing my experiment. But this is unquantified and difficult to control because there is no definite formula for this phenomenon. A possible formula would be the von Mises yield criterion, but it was beyond the scope of this problem, so I ignored that parameter. So the theoretical optimization for torque will be to maximize rigidity, because thus I can maintain the 45 degree in my slant angle. And 45 degrees, as you can see from sine 2 theta, cosine theta, would maximize torque. So my setup involved a paper spiral, a wire to minimize the friction between the center of rotation and the spiral. I also have a wind block, because wind dispersion is unquantifiable. There's probably an equation somewhere, but it's also beyond the scope of this problem. So I obviously, with the wind block, because without a wind block, the wind is inconstant, so it's just not testable. And without the wind block, sometimes the wind isn't even strong enough to spin the spiral. So obviously, a wind block is required for this experiment. Yeah, and the theoretical optimization for wind dispersion would be to restrict it with a wind block such as this. So first, I tested different radii. So I have a thicker spiral with a less average radii. I also have a thinner spiral with a greater average radii. These are the graphs I obtained from my experiment. The rotational angle versus time of my thicker spiral, as you can see from this graph, it accelerates slower than the thinner spiral. It also travels at a slower velocity than the thinner spiral. This matches our theoretical model because our theoretical model has the sum of the two radii, which is the average radii. It's squaring it, so it makes it way more in the overall equation than the difference of the two radii, meaning that the thinner spiral with the larger R inner, because I kept the R outer constant, so this thinner spiral with the larger R inner would also have greater torque. So our optimization is to maximize the length of the lever arm. I also analyzed the rotation, I compared the data points, the data graphs to my theoretical graphs. Because I did not include air resistance, that's why it diverges at the end. So I'll only be looking at this front part, this initial part. As you can see over here, the two graphs don't really match up, and that could be due to human error or some other error. And with the thinner spiral, they do match up. It's pretty accurate. I also compared different heights. I have one spiral located 37.5 cm above the flame, and one spiral located 29.5 cm above the flame. As you can see from the graphs, the spiral located lower, it spun faster, but it also accelerated slower. We think that this could be due to the spiral located lower above the flame, it reaching terminal velocity faster. Because so after it reaches terminal velocity, while the spiral located higher above the flame has not reached terminal velocity yet. So the overall quadratic fit would determine that acceleration for the taller spiral to be greater than the acceleration for the lower spiral, because it has less of a distance that it has less of a time that it's been in terminal velocity. So our experimental optimization would be to minimize the height of the handle. That should also be pretty obvious. And my conclusion. So for optimization, the most relevant parameters are wind velocity, which I can change by adding more handles or having more powerful handles that generate more heat. I also have my area of interest, how much air is hitting the spiral, and the length of the lever arm, which is like the radii of the spiral. Rho air density is negligible because, as I explained, I can't really test this. What I can do is test it in a colder room versus a room temperature room, because in the colder room, the difference in temperature would generate a difference in air density, and with the greater difference in air density, the air will also travel faster. So that is a future experiment I could do. I did not test slant angle because, as I explained in the rigidity slide, slant angle is uncontrollable due to the paper softening from the heat, and the heat is also and the rigidity part are unquantifiable. So I did not test this either. I cannot optimize this either. And these are my citations. Thank you.
Questions from the opponent.
Okay, now I'll start with my cross-examination with the reporter. So first I would like to ask that you assume that the candle within wind block you made is all like flowing up in the same direction. Yeah. So is it a laminar flow? Yeah. Okay.
Oh wait, no. From the candle, the heat should not be laminar flow, because the candle is from the what's it called? The convection currents. It should actually create vortices along the.
Yeah. And how can you assure that all the hot air that is flowing up is all in the same direction?
How would that matter in this problem?
Do you have any proof to your statement about like all of this flowing in the same direction? Because if it's a laminar flow, or even if it's a turbulent flow, it might have different effects on the maximum torque.
Well, if it's turbulent force, then it matters. Turbulent laminar flow should.
Okay, thank you. And then so in your overall experiment, you just neglect air resistance at all?
Yeah.
Okay, thank you. And can you turn to page 16? So your equation is derived from the assumption that theta is constant.
Yeah. No, I never said that.
But you said.
I said theta was uncontrollable. I didn't say it was constant.
Oh, okay, thank you. And yeah, that's the end of my cross-examination.
Please. Yeah.
Okay, honorable judges and worthy reporters, I'm the opponent from Team Palace, and today I'm going to problem number 13, Kendall power turbine. So this is the problem statement, and the focus is that we're going to maximum torque and the effect of Kendall and spiral and theoretical highest angular velocity formula. And this is our outline. So first I'd like to summarize up what the reporters said in their presentation. So their theory is that linear drag with slope law are negligible, and quadratic drag with relative equation is their main theory for the Kendall power turbine to reach its terminal velocity, and they have considerable and they also put into vorticity. And the parameters are different air density and wind speed and radii and slant angle. And their conclusion stated that thinner spiral rotates and accelerates faster than the thicker spiral. And spiral suspended lower rotate faster but accelerate slower. And for their maximum optimization of the torque, they set to maximize the length of the lever arm and minimize the height. And this is their second, and we like to point out their strength and weakness. So for their strength, they have clear explanation of theory, and they use graph to illustrate the phenomenon, and they distinguish the implicit parameters. However, for their weakness, they have mitigating outside factors without clear explanation. And this is what I'm going to discuss with them later. And they also didn't measure the airflow. And without measuring, they just simply assume that it's flowing in the same direction, which we think is a bit problematic. And they did not mention the convection of the air. And this is a brief introduction to what I'm going to discuss with the reporter. So for the experiment, I would like to discuss about the effect of air resistance and the comparison with drag force and air block. And the position of the Kendall and equation and the theta, they have mentioned that they could not even measure it. And the procedure details. And also some of the theory about the equation and theta. And now I'd like to take forward my discussion with the reporter. Okay, so as I mentioned here, I would like to first point out air resistance. So our group actually thinks that air resistance can be one of the determining factor to the maximum torque, while you said that you neglected. So let me show like a simple experiment. So if I'm dragging a paper with even a very slow velocity, you can see that there's actually an angle here as formed by air resistance. However, when doing this, the spiral is made by paper, and you just simply neglect all air resistance.
Well, because I'm optimizing. I'm not trying to quantify the maximum torque. I'm just optimizing.
Yeah, but however, air resistance can be directly proportional to the square of the velocity.
Well, that would matter for every single spiral. So in comparison, all the air resistance cancels out. Because I'm trying to find the fastest spiral. I'm not trying to measure the torque of the fastest spiral.
But I would think that to reach its terminal velocity, it might be affected. If the condition for it to reach the terminal velocity should be like the force from the heated air when the force from the heated air equals to the air resistance provided by the spiral. When it's reached equilibrium, it will reach terminal velocity. And we think it's determining factor for it to examine its maximum torque.
Yeah, sure, but when you're comparing two spirals, the air resistance, they both depend on the velocity. Like look at this. Okay, so I have this first spiral, I name it X. This second spiral, I name it Y. Air resistance, let's say it makes it, I don't know, 0.8, 0.8. If X is bigger than Y, then X is going to be bigger with air resistance regardless. It's still going to be bigger than Y. It doesn't, in comparison, it doesn't matter.
But however, well, until I explain more about the X and Y.
Oh, that's just a dumb example. It's just if a spiral is generating more torque than the other spiral, and you add air resistance onto that theory, then the spiral originally generating more torque is still going to generate more torque. Except the torque is going to be less, but it's still going to be more torque than the other spiral.
But if you're considering the cross area of different spiral, then the air resistance is going to be different. And we didn't see like you consider different spiral in your experiment.
I did. Then you included on your own slide. I had compared like a thinner spiral and a thicker spiral, and also compare different spirals on different heights. But the air resistance is gonna be
But it's gonna be affected by the contact area of the hot air and the surface area of the paper spiral.
and I did include it in my theory. I did include area of the spiral in my theory.
Okay, and next I would like to talk about the air block self-image. Like, can you show us like your experimental setup with the
Yeah.
I mean the one with this one. Yeah. Thank you. So in our cross examination, you said that you assume that all of the air coming up will be coming up for the same direction.
Yeah.
But if here has convection, then the cold air would simply get inside, and you have the hole. So is that there's hole in here? So
Okay. So you have air coming in here, but without the wind block is also for blocking crosswinds. Without crosswinds, the flame and the air only has one direction to rise in. Like
if the air is rising up, it will also flows out of the wind block as well, because they have convection. So when cold air comes in here, hot air will go up, and it will have convection, and some of the hot air might flow out. So it's not going to be in one direction.
Well, if it flows out, then it's not going to affect the spirals. The spiral is directly above the area of interest, as I said. So only the rising air which the spiral is.
And then how can you make sure that it's in the in the same directions? Air might be flowing like with angles, even upon here.
Oh, that was one of my parameters, like air dispersion. But air dispersion is proportional, like how much the air disperses is also proportional to the area of the spiral, because the larger the area, the more air attaches, right? So that is one of my parameters. Area is one of my parameters, so I kind of do take into account the dispersion of air.
Okay, thank you. And next, I would like to talk about the theta one. Can you show us your equation again? So you said that you cannot simply calculate this one,
yeah,
or measure this one out. And how do you prove that this equation actually fits into the real situation?
I cannot calculate that because I'm assuming that all my spirals are relatively the same, have relatively the same data. I cannot calculate that because because data in the experiment is constantly changing. The heat softens the paper and it comes down. So data is always changing.
And do you have any real experimental proof to say it out?
Well, observation is more than enough to do that. If you can see a spiral slowly dropping down, then you know it's not dropping down. You don't need an experiment to tell that the spiral is dropping down.
Okay. And about the position of the candle, you only consider its height, or do you also consider how you place the candle?
Well, if you look at my theory, if I move the angle away from the flame,
yes, then
the area of interaction, like the area of interest, will also change. It will decrease. So of course you want all the air to hit all the area.
But
you don't want.
Have you ever considered moving the candle out from the middle, and you maybe consider it from around it to that the hot air maybe have some influence to the paper spiral?
I considered it, but I didn't experiment with it. I did not experiment with it because it should be pretty obvious that if the area is like this and you move the candle away, so only a tiny bit of the area is hitting, then the torque will be much less than if all of the area was being hit with the air. That should be pretty obvious.
Okay, thank you. How will it affect the terminal velocity if you move it away?
Terminal velocity, it should not affect, because the area is the same, it should not affect terminal velocity.
But the hot air, the force generated by hot air is different.
But the air resistance, the only factor in air resistance is the area of the spiral, the area that is being dragged. So why would the hot air being different affect air resistance? Could you explain that?
The torque might not be the same if you put.
The what?
The torque
Yeah.
might not be the same if you put the candle like in different position, and this might also affect.
The torque could be less though. I'm optimizing it. I'm not trying to de-optimize. I'm not trying to find the least torque. I'm trying to find the most torque.
And do you have any proof that if you place the candle in the middle, it will be the utmost like obvious? How do you know that it's obvious that when you put the candle in the middle, it will be faster?
Well, from my like I said, from my equation, from my theoretical equation, it takes into account area. Its torque is directly related to the area. So if you decrease the area, the torque also decreases. If you increase the area by putting it directly over the fire, because they'll be in a maximum area, then torque will obviously also increase.
Oh, and I have one more question. Like, well, do you think that color will affect the result, the color of the paper spiral?
Well, color might change the rigidity because if the colors are darker and it absorbs more heat, that might soften the paper even more. However, because like I said, rigidity was not quantifiable, so in my experiments, I wouldn't really consider color.
But you just said it might affect the rigidity faster, so it might reach the terminal velocity faster.
Yeah, it might.
Okay, thank you. That's it.
That's only if you're using a dark color, because dark colors absorb heat.
Yeah, I'm asking about different colors.
Yeah.
Thank you. Okay, so in conclusion, we have discussed about air resistance, but there seems to be no understanding between us. Like we think that air resistance will affect it, but while the opponent thinks it is not really a terminal factor. It's not really a determining factor. And also we have discussed about air block, but the reporter team, they suggest that by putting the candle in the middle will create the maximum torque, while we think that they should also conduct experiments with different position of candles. And finally, for the for the equation and the theta about that one, they simply said that it's immeasurable, and we think, and they also think that with different colors, it might reach the terminal velocity faster, and which we would agree with them. And that's the end of my conclusion. Thank you.
Good afternoon, fellow honorable judges and fellow delegates. So I have some questions for the reporter and the opponent. How did you calculate for the drag coefficient that is being used in your theory?
Drag coefficient.
Is it through experimentally or is it through a theoretical calculation?
Theoretical.
Okay. So how many candles do you apply in your experiment? Because it is not shown on the lecture video.
I use one.
One, okay. So how did you make sure that every lap of the spiral is being kept at 45 degrees?
That's why I said it wasn't, because that's why I said
okay, thank you. Do you think the angle should be kept constant?
No, we don't think that it should be kept constant.
Okay. What is your definition of height in the experiment? The height from the spiral to the
I measure it from like the wick, like you know how candles burn on wick, like the string.
How do you think they should be measuring the height?
From the flame.
Okay, thank you.
Yeah, it's the main source of hot
Okay.
heat.
To what extent does the difference in the laminar flow or the turbulent flow affect your result?
Could you please repeat that?
To what extent do you believe that the turbulent flow or the laminar flow will affect your results?
It will affect it, but it won't affect that much because.
Okay, yeah, thank you. How about the?
So like turbulent force is counterclockwise and it's in like different direction, while
Yeah.
laminar force is
To what extent is okay? You do have.
So with laminar force, it might reach
Is it large or?
it will be larger because
Okay.
yeah.
So how is the theta that you use in the equation defined? Because that since the situation that you premise on, you have a graph, kind of like a picture that you show that when heat flow heats the spiral and it bounces back to another direction. However, this bounce to the another direction is premised on the fact that this collision should be perfectly elastic. That then you can say that theta is being defined there. So you neglected the part that where the theta is being constantly changed. Do you think you should consider this theta and aggregate it into your theory rather than just neglect it?
Well, my theory states that theta should be kept at 45 degrees. My theory also states that.
However, you neglected the fact that it is constantly changing.
Because experimentally it's impossible to keep it at 45 degrees.
Yeah, so do you think you should try to fix the angle or rather than just neglect the angle?
Well, I've tried and it's impossible.
Okay, thank you. Then, how is your red eye that you have been changing in the experiment?
My red eye?
The red eye, radius.
Oh, radii. Could you repeat the question?
Good afternoon, honorable judges. I'm the reviewer from Mingdao May, and the problem statement, with the discussion point for the problem statement is how to maximize the torque. And the summary for the reporter is that they used Stokes' law and Rayleigh's equation and torque equation to calculate for their theoretical data, and the relative parameters are the wind speed, radii, stand angle, temperature, and area and height ratio. So the overview for the reporter is that advantage that they have an overall logical presentation, and the demonstration video was being well presented, and the experiment is being well carried out, although there are a lot of control variables that are not being considered. And for some suggestion that we would like to give to the reporter is that there are many relevant parameters that would not be considered, which is such as the laminar or turbulent flow or the angle of attack from the heat flow from the candle, and the parameters that are being changed that would lead to other changing is the supposed control variable are not being controlled, such as when they are changing the radius, the mass would also be changed. And they did not show how some of the parameters are being measured and controlled. And they neglected important variables that would affect the results, such as air resistance, which you can see that there is a big difference in their theoretical data and their experimental data. And their maximized torque would is based on a lot of consumptions that they didn't really have calculate the actual torque, which I believe that didn't 100% to answer the problem. And the overview for the opponent is that they capture some error that is being presented in the experiment, and it is in summary for the reporter's report. And suggestions would be that there are flaws in the experiment that they did not cut the flaws, and like the varying mass and the angle of attack when changing some of the parameters, and they ask multiple trivial questions that were being answered on the presentation, and they are wasting some time. And there are flawed and insufficient theories that were not caught by the opponent. So for discussion 1, the opponent asked how would you describe the flow? Is it a turbulent flow or laminar? And the reporter didn't have a direct answer to this question. So we believe that there should be a turbulent flow that it can be absorbed from the wobbling spiral. And if they calculate for the omega, we can really see how the omega will be fluctuating. And the opponent asks that what is an exact air resistance, because the reporter said that they are not optimizing the torque, not quantifying. I'm optimizing the torque, but not quantifying the torque. But however, we believe that air resistance is one of the most important parameter that they should consider in there. And the opponent said that there are holes on the air block shouldn't it affect, and of course some airflow will escape. And we believe that the wind block will affect the motion. And have you considered the color of the spiral? Can it affect the heat transmission? And they say yes, the darker the increased heat transmission. However, we believe that transmission will be only affected by when the heat is transferred through radiation rather than the heat flow. And some points missed by both the reporter and the opponent. The reporter did not consider the effect of laminar or turbulent flow and the effects of the not controlled variable that is presented in their experiment. It is not discussed. And the correction of the theoretical data should be discussed, since that there is a very big difference in the experimental data and the theoretical data. And the calculation of drag coefficient is missing, since that they said that the drag coefficient is being calculated through theoretical equation, but such that the equation also includes the drag force, and you have to calculate drag force through drag coefficient and drag coefficient through drag force. Thank you.
So my concluding remarks are that first I would like to address my statement about air resistance not mattering. I didn't say that. I said it does matter, but when we are optimizing stuff, why would we include a variable that is the same for every spiral? And for color, darker colors would decrease rigidity, because darker colors would absorb more of the heat, and this will make slanting angle even more volatile. So white is obviously the most controllable color to use. For laminar and turbulent flow, laminar flow would increase torque, but I believe that it is very small, so that's why I did not test it and did not include it in my presentation as well. My height definition, because I think you might have misunderstood. So I defined it as the spiral above the wick, but all the flames I use are the same height. I measure the height of the flames itself. All the flames I use are the same height, so technically the flame is also, my spiral is also the same height above the flame as the wick. And you talk about calculating the maximum torque. I don't see why that is necessary, because I already said this. I'm not trying to quantify the maximum torque. I'm just comparing different parameters to each other and trying to find which parameters give the maximum torque. And keeping theta constant. You talk about keeping theta constant, and I'm saying that it's unrealistic, because in the problem statement it says to use paper. And if you can name one type of paper that is not affected by heat, does not drop down because of heat, then good for you. And that is about it for my concluding remarks.
You finished? Okay, thank you very much. Okay, questions? Maybe.
Yeah, of course, this theta is, I think it's very important. You can actually manipulate it just like a cardiac and bend it like a turbo. But let's consider an ideal situation, no deformation and the steady airflow and so on. Just consider this is spiral. So do you think if the spiral has uniform width or has a variable width, which one will give you a larger maximum torque?
Wait, uniform what and variable what?
This is spiral.
Yeah.
Uniform width or the variable width as a function of theta angle.
So like you mean like as the angle gets larger, the width also gets larger. I think that it will still depend on the area, because if the angle is kept constant and the area is the same, it doesn't matter if one part of it is larger than the other.
No, the spiral is under gravity.
Under gravity.
Yeah. So it's an angle
But you just said
where it
you
depends
just said to
on
keep-
where its position is, because it will be subject to different gravity mass.
Didn't you just say to keep theta constant?
Maybe another.
I wanted him to
From high
answer
school
too.
physics, we all know torque is defined as what? As the radius
So what is defined?
torque.
Torque. Oh, torque is defined as a radius times the force.
Yes.
The acceleration.
Or you can change to the moment inertia times
Yeah.
the acceleration, right?
Yeah.
Angular acceleration. So there's a way to measure torque, even for this spiral.
Yeah.
So you write down, you get an equation, and under an ideal case. So my question is, you really don't know if that equation is correct. Am I right? So because you only measure in that equation, the important parameters are R outer and R inner.
Yeah.
That's it. Plus the slight angle, but you use.
Oh,
You fix it.
and also wind speed.
Yeah.
Wind speed.
So you think only these two parameters is enough to calculate a complicated system
Well, you-
like the spiral?
You can derive a lot more parameters from the initial, because these initial parameters, like for example, velocity, you can also measure the difference in temperature between the
No,
group.
I mean, you really can measure the torque in a sense. As I mentioned, you can determine the moment of inertia
Yeah.
roughly, and you can measure the angular acceleration. So you can measure the torque.
Yeah.
So why didn't you do it than just using an equation to say, okay, this is the maximum?
Well, that's because I'm optimizing. So if
No. That's my question. It's a very complicated system. So this equation is for ideal case,
yeah,
right?
yeah.
But in real case, it may not be correct. So why didn't you measure the torque directly and tell us, okay, this is the optimal setup?
Because if I show that one parameter, increasing one parameter makes the torque larger, then obviously increasing that obviously
The problem says to optimize.
yeah.
So,
It doesn't say to quantify the torque.
no, I agree. But how do you know? By changing only RO and RI gives you the maximum torque. That's what I'm trying to.
Oh, okay.
Because you really didn't measure the torque.
Yeah.
So how can you say, okay, this setup is the maximum torque? Is the maximum torque?
Well, I feel
You
like
say that.
overcomplicating the equation is also beyond the scope of this
Yeah,
problem.
that's what I meant. You measure the torque and then you give the answer. For example, you can change the size of your spiral. See if you give a larger size spiral gives you a bigger torque, or a small size gives you a bigger torque. So you know.
That was one of my experiments, though. Yeah, this is one of my experiments.
Okay, maybe we can have some more
Okay.
discussion. But sorry, I interrupted the first question.
I just want to hear the answer.
The same question.
It's a spiral. Can you get better torque by making this a spiral width not constant but a variable?
So I think if you change the width, it will also change the radius of the whole spiral, which would also change the torque. But if the width is being increased, that the mass would also be increased. That the whole aspect ratio will be different. The length of the whole spiral system will be different.
How could it change the spiral width?
You mean-
You're cutting from the same.
Yeah. Cut. If you print it out and cut it with a larger spiral, that the width is being.
No, the total size is the same. I'm talking about the
Oh, the
spiral
total.
width.
We think that maybe with smaller radius, the total torque will be larger.
Smaller width.
Yeah, for the width. Yeah, because we have done we have conduct experiments too, and we have made a spiral with a constant width of 2 centimeters and another one with only 1 centimeter, but the total radius is the same. And the one with the small radius, which is 1 centimeter, actually spins faster than the one.
It's still fixed width. I'm talking about when you make the width.
You mean like making it with
changing?
So like it's maybe start from 3 centimeters and decreasing to 1 centimeter.
You get better torque that way.
Yeah, we think it is because the area that actually area of air resistance, the effect of air resistance is decreasing because due to like the width is constantly decreasing. So, but however the total surface area that the spiral gain from is actually the same. So we think it might be it might create larger torque.
Okay.
Thank you.
I think the width would, with the increasing different width, I think this would also increase the torque because there's a difference in the angle of attack if you change this width. And I think it's possible that if there's a larger width on the outer side of the spiral, it is possible that the angle of attack will be in about 15 to 20, such that this is the optimized angle of attack.
Wait, could I clarify something about that gentleman's question? I think that if the wider part of the spiral was closer to the fire, that would increase torque, and if the thinner part of the spiral, like what he said, if the thinner part of the spiral was closer to the fire and the wider part is further than the fire, it will decrease torque instead. So it would in fact change torque.
Okay. Thank you. Okay, the scores for the reporter are 5, 7, 6, 6, 7. And the scores for the opponent are 7, 7, 6, 5, 5. And the scores for the reviewer are 7, 8, 7, 6, 6. Okay, then let's take another break.